So basically, there are two computers. There is the desktop computer that is communicating with the robot arms, or the robot arm via its controller box, the black box underneath the table. And then there is my laptop computer that is communicating with the camera above the robot arm. And then there is an Ethernet connection by the blue cable between my laptop computer and the desktop computer.
Okay.
The camera is connected to the laptop computer via USB 3. The desktop computer is running a real-time Ubuntu kernel, and my laptop is running a non-real-time Ubuntu kernel. Reason for which might be explained later, otherwise that will be another video. So basically what is running on the desktop computer is the inverse kinematics and a joint space interpolator, as well as the low-level controllers that take this reference that is generated by the inverse kinematics and the interpolator and convert it into some torques that are then passed on to the joints. On my laptop, there is the node that is running the camera driver, as well as AppleTag 2, that detects the AppleTag that will be moving in the field of view of the camera. Then because AppleTag, the AppleTag node is designed to detect all AppleTags in its field of view, there's an AppleTag selector that selects the specific AppleTag we're interested in. In this case, it's AppleTag with the ID 1. Then afterwards, that pose, because AppleTag knows the size of the AppleTags that it's expecting to detect, so it can it knows the pose, so position and orientation of these AppleTags with respect to the base of the camera, because the camera has a calibration file that enables AppleTag to do that conversion. These poses are then converted from the camera base that is oriented with respect to the camera to the robot arm base. So the camera has a coordinate system that is oriented as such that X is pointing to my left, Y is pointing upwards, and Z is pointing down. But the camera base, or the robot base, Panda Link 0, is oriented with X forwards, Y to the left, and Z upwards.
Yes.
So there happens a translation happens and a rotation happens. This is done in the ROS mode. This transformed AppleTag location is then passed on to a predictive Kalman filter. Then, because the predictive Kalman filter generates a very long matrix of predicted poses, but I don't have a path planner, so I'm just selecting a specific one of these predictions to pass on to the inverse kinematics. Then I have a prediction selector that chooses a specific prediction to pass on, and that is then passed on to the desktop computer. First, on the desktop computer, you open a terminal, Control-Alt-T. Then the workspace that is doing all of the work on the desktop computer is called CKK_WS workspace, because my name is Christian Kamp-Kruse. You don't really need to go into the workspace to run ROS core or ROS launch, but it's convenient if you want to run Ketkin make at some point in the future to do some to do a recompile. Yeah. So ROS core. Now that ROS core is running and it's connected to the master, we can just make a new tab. Then we can say ROS launch, and then the folder in which like where the inverse kinematic solvers and all that stuff is happening is Franke AIC. And then there are two options that are relevant to this project: the AIC_controller.launch and the MRAG underscore controller.launch.
Yes.
I know the package naming is a bit unfortunate, but bear with me. So the ASC controller is, as the name suggests, the ASC controller that is running under the hood, and the MRAC controller is with the MRAC running under the hood. The inverse kinematic solvers are the same, and so are the trajectory interpolators. Before we can run any of these controllers, we first have to turn on the robot arm. That is done by disengaging this emergency power off button. So pull this up. So yeah, so it's the distance is large.
I just pull or do I have to twist?
Just pull, and then we can see over on the robot arm that these lights are flashing yellow. That means it's in the beginning of its startup sequence. Once they are consistently yellow, then it means that it's ready. So continuous blue light means that all of the joints are locked, but that it's ready to, that the joints are ready to be to be unlocked. Once it's done booting, then you can go to this IP address, 172.16.0.3, and then a user interface of the robot arm will be visible, and you can then unlock the joints and activate Franke FCI. It takes about a minute or two to start up, so maybe we can pause the video. So, back again. The yellow light is now on all the time. So if we reload the web page, just pressing F5, then we are now in this user interface. The important things are that, as you can see here, the gripper is red. That is because it's not connected to the robot arm at the moment. If we film the robot arm,
This is over here?
yeah, so over here we can see that all of these joints are white.
Okay.
Except for the gripper, that is red.
Yeah.
And that it being red means that it can't connect to it for, I would say, obvious reasons. It's not there.
Yeah.
So, but the other thing is that the way you unlocked it is simply just by pressing, like here on joints, you have this lock, and you press the unlock. Then it says open failsafe locking system, and you say open. Now it starts opening the joints, and like it takes a little bit. Okay.
All right.
Now the joints are unlocked. So another thing that took me a while to figure out was that the robot arm has two modes. It has ready mode, which is when the lights are blue, and it has the guiding mode, or typically free moves mode, when the lights are white. The way you switch between these two is by using this e-stop button. So when it's engaged, it's in the guiding mode. I've written free moves because I never changed it from free moves up here. So here it's in free moves, but it is actually guiding mode. So when it's engaged and the lights are white, it is using this guiding mode, whichever of these four it may be. But when it's disengaged, it's in ready mode. And ready mode means that it can take external commands, but only, or it cannot accept external commands. It can run programs, but if you want to control it with the FCI interface, the Funke control interface, you have to press this FCI, activate FCI, and now it's activated.
Okay.
And that means now the controller box will accept commands from ROS, from its ROS interface. Yes. Now we can go back to the terminal that we had running before. So the ROS master is still running, and we have the ROS launch file with the Franke active inference controller. So if we start that up, then it should just start. Yes. And then we can
So what did you just check when you look back?
I checked to see if the robot arm didn't move. So as part of the initialization, like it's just like 2 or 3 lines in the code, I set the initial reference position of the robot arm, like the reference positions to its current position. So, like, just in case something got messed up or something, then, like, yeah, I just wanted to be sure.
Okay.
But yeah, that was all I was checking. Now we can launch the other half of the program, the stuff that is running on the laptop. So that happens in MSC underscore workspace up there. Also, it's not necessary to go into that into the workspace. It's just convenient. Let's launch, and then I've there are many sub packages in on this side of the program, but I've made like a top level package that is just a launch file, and that is a non-real-time launcher, because everything in this computer is happening in non-real-time, and everything in this computer is happening with the real-time operating system. So, and there's only one launch file, and that is object detect select predict the launch.
Okay.
And basically, what is happening here is that the RQT image viewer is displaying the images that are seen by the camera, and it's overlaying them with the tag detections from the able tag. So there's like a faint outline of able tag 1 over here. It's more visible if we put more able tags in the image. But what is also happening is that Arvis is launched, and here we can see all of the coordinate systems being used by the program. So there's the camera frame and the tag 1 frame, and then all of the frames used by the robot arm.
Okay, so
The frames used by the the camera frame from the robot arm are a total mess. So don't worry about that right now. But yeah. As you may also be able to see, is that the camera is pointing the opposite way of the able tag, but the end effector coordinate systems are pointing roughly the same direction as, or like the z-axis. It's RGB. Oh yeah, important point. RGB for X, Y, and Z. So the red is X, green is Y, and blue is Z. Yes, that's so yeah. What's happening here is the camera detects the able tags and then passes the locations on through the pipeline. But as you may have noticed, the robot arm is not going for the able tag right now, and that's because in the node right before, like in the, I think it's in the prediction selector, I determine if because everything is happening in the coordinate frame, coordinate system of the robot arm space, I can say if I see that the able tag's distance from the base is further away than what the robot arm can reach, it will, instead of passing on the detected coordinate, it will pass on some default coordinate, the one that it's going to right now.
Okay.
To like a safe-ish location.
Yeah.
Then as soon as the able tag, or the prediction of the able tag, gets within reach of the robot arm, it will then try and go for that prediction.
Okay.
So, let's do it in a similar safe manner. So, that's cool. That's basically how it works.
Yeah.
And like initially, I was using just the predicted position, and I'm still just using that in task space. But when because the inverse kinematics solver only does inverse kinematics, it doesn't do inverse dynamics. So I'm not using the predicted velocities for anything right now. Yeah. But I'm still from the joint space positions that are generated by the inverse kinematics. I use those to generate velocity references, and in the MRAG I low pass filter both the position reference and velocity reference because the MRAG was a pain in the ass to shoot. But the ASC is Yeah, it's fun to play with.
Yeah.
But the AAC is, yeah, it didn't require that I low pass filtered the references. It even got a little unstable when I tried.
Yeah.
So when the inverse kinematics calculate a reference position, I differentiate that and generate a velocity reference in joint space. In the AAC, I don't low pass filter it. I just say present position minus previous position divided by the sampling frequency or sampling time, which is 1 kilohertz, by the way. But in the MREC, I low pass filter it. Yeah, and when I did that, it did, like, the MREC and the AAC got slightly more, I want to say, oscillatory. I'm not entirely sure. I have not analyzed the adaptation parameters super thoroughly. I just used the plots of the internal dynamics to get them to work. But yeah, so like normally when I just turn on the conveyor belt to pass the APTEC through, then it would then the AAC would move to right above the APTEC and slow down. But when I included the velocity reference, it had a tendency to have an overshoot. And the problem with overshoot is that then when it bumps into this stack, then it gets a I want to say torque error because it experiences torques externally that it isn't expecting, and then it freezes. So that's why I, instead of using this block as the target itself, I disable the robot arm, pass the APTEC through to roughly where the robot arm would intercept it, and then I block the APTEC so that I ensure that it's only the common predictions that are being used without measurement updates.
Yeah.
And that's also how I made the measurements for the report. I've set the measurements into the report now, so you can see them. They're not finished, but like the lines and stuff are there.
Okay.
So like it might overshoot and hit the block and stop, but we can try and see it in action now. So it's the conveyor belt is set to 2 right now. So yeah, and now because the common filter's main purpose is to prevent the robot arm obscuring the target from stopping the robot arm, and we can see that the robot arm is tracking the object roughly. So we can see that the robot arm continues because it thinks that the velocity is like it's making it go in that direction. And now when the predicted position went outside of the reach zone of the rover, it went back to its swimming position.
Okay.
Also, the reason, like, before I added the velocity reference, I just used this foam block to distance the APTEC from the conveyor belt as a safety precaution. But now that there was overshoot, especially with the MREC, but also with the AAC, and now I'm looking at the measurements, the AAC has some pretty wild overshoots as well. I added this extra buffering so that when I used was back to save the data and then it was played to play the data again, then it would have a couple of some more centimeters to overshoot with.
Okay.
That's the reason for the very large stack.
Yeah. Okay.
I think that's basically it.